We're going to continue on with our work, covering radicals. And by the time you leave here today, you ought to be very good at simplifying, adding, subtracting, multiplying, and dividing radicals. This is 3.2, solving quadratics. Solving quadratics using square roots. So we got to be good at square roots. So radical times radical, yes? So what's the only requirement that we've got for this? Same root. Same root. The radicands don't have to be the same. We just got to have the same root. Do we have the same root?
Yeah.
We sure do. It's a square root times a square root. Good.
So the root is inside the square root sign, and then the radicand is the 2 and the 4, right?
There we go. And then coefficient.
Yeah.
Am I spelling this right? Coefficient. I don't know.
So, but we need the same radicand for adding and subtracting.
Yes, sir. So add and subtract, you got to have same root and radicand. With multiplying, you just got to have the same root. Okay. Good question. We got to make sure we got our terminology down, Pat. Now, in this case, a fool would be one to say, oh, coach, just multiply 2 times 4 and 35 times 7. Right? Now, 35 times 7 will be what, 245?
Yeah.
Right? I don't know what the square root of 245 is, but guess what? I can say 2 times 4 is 8, and then I can just write 35 times 7 as the product. Don't actually do the multiplication because I'm seeking Aiden to do what to that radical? I want to simplify. I don't want to complicate it. Now, BJ, what's 35 the same thing as? So I got 5 times 7 times 7, and lo and behold, there's a couple 7s in there, right? So 35 times 7 is the same thing as 49 times 5. Square root of 49 simplifies. Or if you like the Jailer approach, which I speak about a little bit before, this number right here, that root, is like a jailer, and he says, hey, if there's this many of you, I'll let you out of jail. Woohoo! And so they get out of jail. 8 was the coefficient. You write it once. 7 got out of jail. Sorry, 5, you're left in jail. And so what does that wind up equaling? 56 square root of 5. Now, I'm very well aware of the fact that I can hold up a smartphone to this problem right here, and like Photomath, for example, could tell me 56 radical 5. Okay? Like, I get that, but that's not helping me at all. Okay? Because I've got to be able to go through this process. In my brain, I've got to understand the math. Oh, perfect. Okay, so I like to explain this 2 different ways, Sebastian. One way, which is probably the more conventional way of explaining it, is to consider writing it as a product, right? 8 times, what did we say it was, 245?
I get that.
Gotcha. So you're comfy with the conventional, like, kind of green way? Hold on, we got a question on the floor already. All right, so this green way you say you're comfy with, you're happy doing it that way? All right. This alternative way of sort of looking at it would be to say anytime there's a square root and you've got this written out as just a long list of factors, if you ever see a couple of identical factors, you can get those out of the radicand and just write that pair of factors as one coefficient. Yeah. And the reason I sort of like that approach, Sebastian, is it helps me, and I'm just kind of like this. It helps me with these problems. Like if I had 125 x to the 7th, then I could sort of think about that as 5 times 5 times 5 times x, and then I can go through and cherry pick out the pairs because it's a square root. And I would say, okay, that's 5x cubed that's on the outside and 5x is on the inside. Because I see I'm getting rid of these pairs, and then 5x is left over on the inside. How many pairs was it? Well, it was 1 pair of 5s and then 3 pairs of x. That's an alternate approach that, in my opinion, sometimes visually see it. Now, if this was like, x to the 730, I'm not going to do that many x's. But if it's reasonably small number, and where that also plays in nicely is, what if this was 625 and this was a cubed root? And so now all of a sudden I'm not pulling out and this isn't just Sebastian's question. I'm talking to everybody here. Now, oops, I'm not just pulling out pairs. I'm pulling out groups of three, pulling out triples. So there would be a set of 3 5s, couple of, so this would be what? 5x squared cube root of 5x. So sort of that jailer approach. I call him the little number on the ledge. He's like the guy that's in charge of the jail. He's like Barney Fife. Can you see my Barney Fife over here?
Is that what it's called?
No, that's what Coach Moore was talking. Yeah, one of my favorite shows. Coach Adam Smith's favorite show as well. Andy Griffith show. Barney was in charge of the jail all the time, and so you can imagine that little number up on the ledge. He's like a jailer, and he's like, "Oh, sweet, there's 3 of you guys. Y'all get on out of jail." All right, Ken.
Oh, so I was really confused, like, it would be like, say, with a square root, to be able to, and so you have x4, you just take out all the x's, but you don't leave anything to radical, and the x squared on the.
Yeah, so you're saying square root of x to the 4th? Yeah, so you can look at that like there's 4 x's in jail, and you can pair them up 2 and 2, and so it would be x squared on the outside. Now there's another way of looking at this, and kind of talk about radicals. Andrew, do you remember what the phrase that pays is? Ooh, Phil, what about you? Right. It is something over something. Phil, what's the phrase that pays? Anybody know? All right, so here, check this out, fellas. This is great. This is perfect. Y'all are learning lots about radicals today, or relearning lots about radicals. Check this out. So in this same context of what Buckhold and I are talking about, suppose I have the rth root, and I've got my base raised to the p power. What do you think, Andrew? The phrase that pays is power over root. So you could express a radical as a fractional exponent. We do this in calculus all the daggum time. Okay, so like in calculus, I might have the square root of x. There's your example, okay? I might have the square root of x, and my calculus teacher might say, take the derivative of the square root of x. That's really hard to do that in its radical form. But if you convert it into exponent form, if you convert it as x to the 1/2 power, then you could use your power rule. And the power rule for calculus derivatives is way easier than the radical rule is. Okay. And so being able to convert using that phrase that pays, Andrew, say it one more time. Power over root. Did we write that down? Power over root. That's another way, Sebastian, that I could maybe tackle one of those problems. Like, for example, the cube root of x to the 7th, I could think that's x to the what fraction, Mr. Green? Power over root. Power over root. What's the power that x is raised to? Good. What's the root? Try 3. There you go. So that's x to the 7/3 power. Right? And so just another little nugget of information for you that kind of comes up in discussing radical. Finley, what do you want? You want to go? Oh, good, great. Hurry up. Actually, that's a nice offer. Thank you. I'll take you up on it. Greenie.
Why is it 1/2? I get the power of x.
And there's an implied root of 2. Fabulous question. Did y'all hear Blake's question? He says, why is it x to the 1/2 power? Because there's an implied power of 1 that we don't ever write. And there's an implied root of 2. Okay, so Christian, help me out. What about the cubed root of x? What would that be? X to the what? Very good. 1/3 power. And fellas, you're opening the door to success in classes like calculus when you have these algebra facts kind of locked down and very readily available in your brains. For sure. Yes. Abso-friggin-lutely. Okay, and watch this. So I'll tell you what, on my graphing calculator, I'll show you a real quick little hack. Like on Desmos, like if you're on Desmos, there's not like a square root button on my keyboard, but guess what? I could raise it to the 0.5 power. And there's no difference whatsoever. All right, so let me quit out of this. Hold up. Main 6. All right, so if I went to y equals and I just want to graph out the square root function. Do y'all remember what we said the square root function looks like? Zoom 6, and then boom, there's my square root function. It's half of a parabola. Did we know that? Square root function is the top half of a horizontal parabola. All right, so look at this. Watch. I'm gonna say, all right, well, how about x to the power of 1 half? X to the 1/2 power. And here, I'll unhighlight my equal sign. Did y'all know you could unhighlight an equal sign so that it's not showing up on the graph? And look at that, same exact picture. And if you wanted to graph them both, just highlight the equal sign, hit graph, and then they graph one right on top of the other. Okay, that's because they're the same exact function. Good question. All right, so regardless, we get 56 square root of 5. We're comfortable with that. We've done adding. We've done multiplying. Did you like the rationalize the denominator type questions? Were those easy? What about the binomial denominators? The ones, did you use the C word? Did you use the conjugate? Let's take a look at one of those. Who's somebody that hasn't done it yet? Franklin, you haven't done yours yet? Perfect. Can we pull? Oh, shucks. Okay, I gotta do it this way then. Edit assignment. Edit that. Skills. There we go. All right, perfect. Here we go. I don't know why I said perfect. Perfect. Put the wrong emphasis on the wrong syllable. All right. Did you get that joke? It's not my joke. It's Jim Gaffigan's. What would be the conjugate, Mr. Davis, of our denominator? Good. Finley, you're taking too long. I'm thirsty, Finley. Where's my water? You filled up 3 bottles? Mulatto. Golly, Pete. Think about it. A bunch, probably. I saw somebody the other day that had put like a little sticker on the sensor and it was just running. And I'm like, really? Low down. You low down, you dirty. All right, what property are you going to use for the numerators? Mitch and Mitchell, y'all get eyes up there and off the calculator. We're going to use the distributive property. Very nice. So what do y'all think? 28 minus 4 radical 14. Now, slow down, make sure I'm not going too fast here. What do I notice, Steve Areno, is common between those two? The two that I've written up, 28 and 4 radical 14. What's in common? There's a common factor of 4. Now, can you tell where your brain should be going at this moment? In just a second, I don't even have the dadgum denominator up there yet. And I'm already thinking, ooh, I wonder if I can factor out a 4 and cancel a common factor with the top and the bottom of this fraction. That's the speed at which your brain should be working. You are thinking like a chess player more than just one move ahead. You're plotting, you're scheming, you're planning. That might not come to anything. I don't know. I haven't done the dadgum denominator yet, but we're fixing to. Okay. What's 49 minus 14?
35.
Oh, shucks. 35 does not have 2 or 4 as a common factor. So we wouldn't be able to cancel. But in another example, you might be able to. Nicholas, did I see your hand up? You're good. All right, Jack, why in the world did I say 49 minus 14? Where'd that come about? In other words, what process do you want me to do on the denominator? Aiden, you gave him some bad intel. Or was that Finley? Dang, Mulatto's not only making Finley his mule, but he's also dogging out Aiden pretty quick. Foil, but what happens to the O and the I?
You take them out.
They cancel out because those binomials are conjugates. And the foo. And that's very nice because the foo is where those radicals would have still been hanging on. The oi is where those radicals would have been hanging on. The foo is just 7 times 7 and radical 14 times negative radical 14. So that's where we get our 35 right there. Okay. I feel like I saw some hands go up. Absolutely. Let me change color. Thank you for asking that, Franklin. So we got 7 plus radical 14, 7 minus radical 14. And I'll go ahead and do the whole kit and caboodle. We'll go ahead and do the whole FOIL. So FOIL. If I see that right. Now, Freddie helped me with the F. Mitchell helped me with the O. Mitch helped me with the I. Fredo helped me with the L. Please and thank you. Go right ahead. Good. 7 times 7, 49. Mitchell Gilmore. What does O stand for? So I'm multiplying 7 times negative radical 14. All right, thank you very much. So I'm going to have negative 7 square root of 14. All right, let's go, Davenport. Good. So I got square root of 14 times positive 7. That's 7 square root of 14. And then, Fredo, you got last times last? And what does that equal? Let's micromanage this thing. It's a positive times a negative. So what's the sign going to be? Very nice. And square root times itself always goes away, and you're just left with the radicand. So what do you think? Just the radicand. 14. Good. So like classes, everybody get that? That's a point that I always end up making in my trigonometry classes. What's the square root of 2 times the square root of 2? What's, Mario, pay attention. What's the square root of 3 times the square root of 3? What's the square root of 5 times the square root of 5? Okay, you get what I'm saying? So square root of 14 times square root of 14 is 14. Now we happen to make it negative because, like Fredo said, it was a positive times a negative. Now, we kind of picking up what we're putting down. The OI is going to cancel out, and bye-bye radicals. Now we got 49 minus 14. That's where we got our 35. Okay. Okay.
So, that applies for every group, right? Like say, cube root of 14.
Oh, no, sirree. You got to adjust your technique. You got to adjust your strategy. Now, on the homework, all they had was square roots. Yeah. If you had a cube root, okay, so let's just pause and consider that. And it was a very good question. Somebody needs to tell me what time this class is going to be over, by the way. All right, so we're doing okay on time. Everybody comfy with this? We're just kind of diving a little deeper into radicals. Suppose I'll make up something real simple. Cube root of 5. So we got 1 over the cube root of 5. All right, Aiden, we're going to make you our sacrificial goat, okay? What do you want to multiply by to get rid of that radical? By the way, this is not meant to be an insult, but I 100% expect you to give me an answer that's not right. So there's no pressure on you. Say it again. Cube root of 5. All right. That's okay. Here's what I want. I want the wrong answer. Somebody's going to give me the wrong answer that I want. All right. What do you think the typical wrong answer would be, Mario? Well, what's with all the negatives? No, it's just positive. Positive. Like here's back this thing up. Beep, beep, beep. What did y'all say worked in this case? Radical 2 over radical 2. Radical 3 over radical 3. Radical 5 over radical 5. All right. So it shouldn't be a surprise that I'm kind of wanting Aiden, I'm kind of wanting Mario to just tell me what? Cube root of 5 over cube root of 5. But here's why that doesn't work. And this is what I was telling Kenneth, you got to change your technique. What is the cube root of 5 times the cube root of 5? Does it do like Fredo's square root of 14 times square root of 14 and cancel out? No, because it's daggum cube root. So this would be the cube root of what? It's the cube root of 25. And we want the cube root of 125 because that's our perfect cube. So amend your technique. What should I put in front of that 5? I'll put a little 2 in front of it. Mitchell, you had a hand up? Oh, beautiful. Good job. All right. So now I multiply the top times top. Kenneth, is this scratching the itch that you had? All right. So now the denominator is just going to be 5. No more radical. We love it. So you're thinking on your toes. Here's where your math teacher has given you a crap load of practice on square roots, and then all of a sudden on a quiz, coming up, he says rationalize this cube root problem. And it's not rinse and repeat, monkey see, monkey do, monkey poop all over you. It's, oh, I've learned this strategy. Now let me maybe tweak it a little bit and use it in this tougher scenario.
So it should multiply the radical by the root. Like to get to 25, all you did was multiply 5 by 3.
You know what we did? To figure out the 25, we asked the question, what would satisfy the jailer? What would satisfy the jailer? The jailer wants how many 5s? And dadgum, we're going to give him what he wants. You know what I'm saying? So like now you could make up some cockamamie, like here, the 7th root of 5 squared. Okay, what would you multiply by to rationalize that? 5 to the 5th. Because the jailer wants how many?
7.
He wants 7, and we're going to give him 7. You already got a couple? Sweet, we'll give him 5. And so it would be like 7 through to 5 to the 5th over 7 through to 5 to the 5th. Okay, and where you're really kind of getting gnarly is when they start introducing variables, right? And you start saying something like that. You know what I'm saying? Exactly. So you would need some more information, but this is not the scope and sequence of this course. But I'm saying like where you're eventually going in these sort of higher powered mathematics classes is you would be asking yourself the question, okay, well, what would I need to multiply to get from 2 to n? And you, again, like I said, you need a little more information there. What do you think, Mike? Yes. All right. Because looking at 25 might not be the best way of looking at that number. Let's look at it as 5 squared. All right. And then down at the bottom, now we would multiply. Remember, with multiplication, as long as the roots are the same, then we're good to multiply the radicands. And so 5 times 5 squared would be, I'll just slide to the right, would be the cube root of 125, which we know to be 5. No more radical in the denominator, so life is good. And so the way that we, sort of attack these problems is we ask ourselves the question, how much do I need in that? And you could practice doing this with multiple factors, not just like a number, okay? But check this out. What if I gave you we'll make it simple. I gave you the square root of x, y. You would tell me I need another x and another y. And then we can start, kind of upping the ante and being like that. And so now we'll throw it back to you, Michael. Like, how much more x would you need? You'd need 4 more x's, and how many more y's? 3. You get what I'm saying? So now we would say, all right, well, I'll just have to do the 6th root of x to the 4th, y to the 3rd over itself. Does that help clear that up, Freddie? Absolutely. Because guess what? Power over root, the phrase that pays, when the power and the root are the same, what does that fractional exponent become? 1, and that's a trivial exponent that I no longer need, and so it's just the base, no more radical, in good form. Thanks.
The practice curveball quiz question.
Yeah.
Yes, hold on. What's the reason behind? Oh, okay. A couple ways of answering this question. Yes, Efkman, I think I can do that. Sebastian, to your point, it's bad form to have a radical left in our denominator. So we're trying to figure out a way to get rid of the radicals. That process is called rationalizing. And somebody asked me the other day, they're like, well, why do you care if there's a radical in the denominator? And I'm like, well, why do you capitalize the first letter of a sentence? Did we use that analogy in here? Right? Okay, so perfect. And it's just kind of like, that's how we do things. But what's nice is when you guys get into calculus, then it'll be like, I don't really care if there's a radical in the denominator. Not a big deal. Heck, sometimes you'll have to artificially put a radical in the denominator to make something work out. So this is really an exercise for you guys to be fluid and be able to move from having radicals in the denominator to radicals in the numerator, binomial, monomial, what have you. Okay, so curveball question. Now, you saw this in my Algebra 1 class, but you might have forgotten. So let's consider this again. By the way, while y'all are chewing on this one, I'm gonna pass out some papers. Number 4, by the way, on this problem set was the most frequently missed problem. The answer was 1 to 6 or 1/6. Had a lot of folks that were in the neighborhood of that. But they mixed in like the letter A or the letter B. I'm looking for the fraction 1/6 or 1 to 6. No A's in it, no B's in it, no nothing. And we can work this out if y'all have questions. But number 4, vast majority of the mistakes that were made were on number 4.
That problem set things.
This was number 5. Y'all turned this in back when I was sick, I think.
Yeah, we did.
Excellent.
The people still on for now use like always gonna be that. NLP. I have to repeat. NLP. Take on the people. They people, those people that
Yeah.
The birth. Just
All right, let's use our hearts. We'll remind me to hit this up on Tuesday when I see it at the beginning of class. We won't have a quiz at the beginning of class. We'll mix it into the middle of class. Thanks again, boys. Thank you too. What you got?
Doesn't that have to be the conjugate